Hi, everyone. Welcome to our talk. I'm Kasimir Schulz. I'm a principal security researcher over at HiddenLayer.
And I'm Tom Bonner, VP of Research at HiddenLayer. So, yeah, we've been investigating machine learning libraries and file formats for the past couple of years, and notice there's a huge problem with the deserialization of untrusted data. We're going to largely focus on Pickle, the more boring format, and R, which Kaz will cover in a bit, the more fun format that I'm sure you're all here to learn about. But by no means is this problem limited to these formats at the end of the day. So why are we talking about Pickle again? I'm well aware it's been done, and perhaps done to death. But Marco Sleviero gave a great talk here about 13 years ago called Sour Pickles. Definitely recommend you check that one out if you haven't before. But in the past 13 years, we've gone through a few Python versions, still a major lack of awareness, and a few updates to Pickle itself later. We still got the big red warning on the Pickle page. We're still seeing Pickle being used to serialize things like machine learning models. We see it used for IPC. We see it used for RPC, over unauthenticated data channels. There's more vulnerabilities than ever. We counted 300 or so in the last year alone. Mythic, Cobalt Strike, Metasploit payloads all using Pickle for stages. But I think the most interesting thing, and why we just wanted to touch on this now, was that anti-malware scanners are starting to get in on the act. So be that commercial or open source scanners. And really we're in a bit of a cat and mouse game where we're trying to evade some of the scanning solutions with Pickle. So that's what we're going to focus on for the first half of this talk. So quick recap then, Pickle, it's a stack-based virtual machine, processes bytecode, interleaves instructions and data together. Very simple, there's a stack. We have a memo as well that operates a bit like registers in a processor. And there are about 4 instructions that really can lead to code execution. So we've got global and stack global that can be used to pull in a method from a module or a class. Instantiate, that'll instantiate a class, and reduce, that will essentially call a method on the stack. So yeah, again, just part of the recap. Here we've got a very simple class and a reduce function. So the reduce function, when we're dumping this using Pickle, will return a callable and an argument tuple. And the tuple is applied to the callable. So in this case, the callable is eval, and we've got a very simple just print pwn string, and you can insert your payload there. So we look at the disassembly on the right. We can see there's a proto opcode at the start. So it's Pickle protocol version 4, a frame opcode, more on that in a bit. And then we push some strings on the stack. So short bin Unicode built-ins, then eval, then we call stack global. So at that point, it's going to kind of resolve the method from built-ins, and the eval function will be pushed on the stack. Then we push on our print pwned, so the code we want to pass to eval, and we turn that into a tuple. And finally, the reduce function is going to grab the tuple and the function off the stack and call the function with the arguments. So pretty simple. Whilst we've been playing around, we noticed a few oddities with the file format itself. So there are some opcodes that aren't required, the protocol version being one of the big ones. Now, in the early days and in the initial talk that Marco did, I believe Pickle was largely a sort of text-based file format. It's now kind of a mixture of text and binary. And in the newer versions, the proto opcode is encoded using byte 80 followed by the version. So if we're using protocol version 4, we'll see the bytes 8004 at the header of the file. So a lot of scanners rely on that. They look for this protocol byte when IDing files. Or some of them are even worse than that, actually. They just look for a .pickle file extension, so they're even easier to evade. So take that away, and certain scanners fail to identify the pickle, which is a lovely way of sneaking your payload in. The frame opcode as well. The frame opcode's largely there to reduce the number of sort of reads in the underlying Pickle subsystem. So you can kind of chunk up portions of Pickle opcodes and read them in one block. I believe that was the intention of that one. Introduced in version 4, but again, not required. And the same with the stop opcode. So all Pickles will end with a stop opcode byte 2e, and you can totally omit that as well. Now, again, scanners check for this, so they'll look for 0x80 at the start of the file and 2e at the end. And although if you omit the stop opcode, both the disassembler will raise an exception. You'll get a value error when disassembling, or the loader itself will actually raise an end-of-file error. I think the important thing to note is that any payload in the pickle will still be executed prior to any exception being thrown. So again, it just makes it a lot harder for security solutions to ID these files. So we're looking at ways to bypass, and a lot of the scanners at the moment tend to have a kind of deny list of methods. So things like exec, eval, OS system, not allowed to see them in a pickle. So we went looking for other methods that we could use, and one of the interesting ones was actually using Pickle itself. So we put a pickle in a pickle, and then use pickle.loads to load it up. Yeah, so in this instance, a lot of the scanners just weren't checking for this. It's a very hard problem. There are hundreds of methods throughout the Python libraries that we can use for executing code. So you're really chasing your own tail if you're trying to make a deny list at the end of the day. After that, we looked at implementing sort of a more pure shellcode loader. So like, I've seen payloads in the past where people have used exec to run a Python script that would inject shellcode into memory, but could we do it using a pure pickle was the thinking. So the plan was to use C types to like load library kernel 32.dll, virtual alloc, write process memory, create thread, very standard sort of injection technique. So what we came up with here, basically here, we defined some shellcode. It's a very simple x64 calc.exe launcher. We've got a few helper classes here that just help to provide some of the flags to virtual alloc and write process memory. And then, yeah, on the right-hand side, we've got the main class. So this will import kernel 32.dll, and then we've got a class for virtual alloc, and the reduce there is going to call into the C types sort of virtual alloc function. Same for process memory, same for create thread. And when we dump that out, we simply save it using an array, and we pass each of those classes into that. And yeah, at the end of it, we load it up, and we get a calc.exe, just using pure pickle at the end of the day. So we'd got that far, and we still felt there was a lot more scope for abuse in the pickle format. We wanted a way to craft pickles that we wouldn't necessarily be able to make by hand. I'd spent a bit of time hacking away in the hex editor, and that was a bit of a pain. There were some limitations with that. So Kaz actually created a wonderful disassembler and assembler. So now we can sort of create highly bespoke payloads, define our own opcodes in any sequence we want, and generate sequences of opcodes that's just not possible to create using the standard Python pickler. So as a very simple example here, we just declare instruction. We've got a nice sort of human readable name, so proto4 or short bin Unicode. And we can start handcrafting pickles. Now, so both of these are kind of interesting because in a normal pickle, if you were to try and use the eval function, you just have built-in eval on the stack via the short bin Unicode strings. But here, because Python is an absolutely disgusting language, there are many ways to access the call method for eval. So we can do built-ins eval.__call, for instance, or we can not reference it through built-ins, we can reference it through __main and then touch built-in. So there are many ways to encode the sort of module and method names that would, again, evade a lot of scanners and their deny lists at the end of the day. That was sort of the purpose behind that. Taking it a step further, we can even construct strings on the stack. So using a more benign method like string.join, we can push like exec onto the stack, string.join it together, then go and resolve it using the stack global opcode. So at this point, sort of simple, just sort of signature-based solutions that are just looking for method names are going to fall short. You're going to need to start doing things like stack emulation in order to potentially spot this. Not content to leave it there, we got to wondering if it was possible to pickle code objects. Now, the standard Python library says you can't. There is a third-party module called dill that allows you to do that. But we started to wonder if we could actually achieve it just using the standard module itself. You can do it using marshal.dump and marshal load, but a lot of security solutions blacklist those functions. So rather than that, we ended up, this solution here will basically dump a code object. So it's sort of one of the base objects built into Python. So we're able to store all of the arguments for the constructor, for the code object class, and actually get it into a pickle. Now this was kind of just a bit of a test to prove that we could do it. What we actually came up with was using the assembler. We can define, well, on the outside there's a function type. So any code object we return, in order to run it, we need to essentially cast it to a function type. But yeah, we can build up the code type class using stack global to instantiate that. We supply the arguments, and then highlighted in green there is the compiled Python bytecode for the code we want to run. So you could swap that out with any payload you want. We do need to grab built-ins.global at one point. So that's used to provide basically the global scope functions to the function type, and then reduce it. So that runs. And again, these function names, we could encode them, we could build them up on the stack, we could obfuscate this way more, but we're just trying to keep things fairly clear. So to help, we're releasing, I should have mentioned earlier, we're releasing the disassembler and the assembler as open source. There'll be some links to that further on in the slide deck. As part of that project, we have got a function in there called create generative pickle. So just to make it nice and easy, you can feed in any function with any payload you like, and that will go and create the sort of function pickle that we just saw in the previous slide. Only caveat is it is Python version specific. So if you make something or pickle something using Python 3.9, don't be surprised if it breaks when you go targeting a 3.12 system, for instance. And finally then, just to wrap off Pickle before we get into the fun R stuff, we wondered if it was possible to attack the Unpickler itself, so like the loaded Unpickler class instance that's actually processing the byte stream. I really wanted to get access to the Pickle data stream. It would have been really cool to add opcodes to it as it was being loaded, but sadly it wasn't possible. The Unpickler only takes a read callback function, so there was no write, there was no buffer, there was no way to append additional opcodes to the Pickle itself. So we had a really good look at the class, wondered, what could we potentially target in there? And the main thing that stood out was the opcode dispatch table. So after a bit of fiddling around, basically what we were trying to do was find the Unpickler loaded class, so the sort of self-reference to the Unpickler should be visible through local scope variables. Then, for a sort of simple demonstration, get one of the opcode handlers. In this case, we'll use load short bin Unicode that loads the strings onto the stack, and see if we can remap it to another opcode. And then we can, for the rest of the Pickle, just encode strings using this new opcode handler. So yeah. Basically, this is doing what we just described there. I appreciate it maybe a little small and hard to read, but we grab this self-reference to the Unpickler class. We via the locals, we find the dispatch table. Then on the right-hand side, at entry 140 in the table, we pull out the existing load short bin Unicode method. And then we patch it back in at an unused opcode, so 56. And then later on in here, we start using our new short bin Unicode opcode. So in our assembler, we just remap that to short bin Unicode bad, for want of a better name. And then we can push built-ins and exec on the stack. So again, existing security solutions, they're not going to be able to parse this. It breaks the disassembler. And there's a few more interesting things we can do with that as well. So one thing to note with that, though, is that there are actually two unpicklers, well, picklers and unpicklers in Python. So today, if you try and use Pickle, it'll actually use the C-based implementation for performance reasons. And that previous method doesn't work for the C-based implementation, only for the sort of Pythonic Unpickler. So yeah, we can use it for other libraries, things like joblib. So joblib will always use a Python-based Unpickler under the hood, so that's a prime target for this kind of attack. And we don't just have to use it for sort of loading up strings. We can combine this with the Lambda and function pickling, so we can actually just create a new function on the stack and then have a new opcode point into that, and then call the new opcode. So yeah, it'd be quite an interesting way of obfuscating pickles at the end of the day. So yeah, that's it for me on the pickle update. I shall hand over to Kaz now for the really fun R stuff.
So as you can see from all of the pickle stuff we did, we got pretty far into pickle. And as most researchers normally do, we got bored with pickle. We wanted to see what else is there out there. So we decided to look into R. So why did we look into R? We decided to look into R because R is used pretty widely by the data science and statistics communities. So that meant any vulnerability that was found in that would actually be pretty impactful. Just like with Pickle, a lot of people use Pickle, especially in machine learning nowadays. With R, there's a wide impact. We also chose R because the serialization format was using bytecode very similar to Pickle. So it's a virtual machine, and we'd love attacking anything that runs code. And then finally, R really hadn't undergone any security scrutiny at all. So there was only one pre-existing CVE in R, and that was by Cisco Talos. And for an entire programming language, that's really not much. So let's talk about the RDS file. If you've read our research, the RDS file, so R data serialization file, is R's version of Pickle. And it's a serialization format, and it's used for quite a variety of things in R. So it's often used for saving workspaces, for saving individual objects. We can use it for sharing data. So let's say I really want to share some data I have with Tom. I send it over to him, and because he didn't listen to my talk yet, he's going to load it, hopefully. We'll see. And then you can also use it for persistence. So that means if I want to save my file, load it up later, I can do that. And when we look at the two main functions that are used for RDS, the save RDS and the read RDS files, we can already notice some of R's quirks. So what you actually might notice up here is that there's an optional parameter called compress in the save RDS file, and that's defaulted to true. And if you set that to false, the RDS file won't be compressed. However, the read RDS file won't be able to read it because the read RDS file can only read compressed data. So as you can see, some oddities already started. And as researchers, we loved seeing this when we were first doing just discovery, because if there's things like that, it's probably going to be fairly vulnerable down the road. So the quirks and inconsistencies continue a bit when we actually go into the RDS file format, which you can see with there's variable and changing numbers up there. So the Good. All right. The RDS file has three main different types. So just like with Pickle, the first type is ASCII, and that's because when R was first made, we had that ASCII format, so just like Pickle. And the way that the R interpreter decides what type of file this RDS file is it tries to read the first 2 bytes and parse them as a magic header. So if it sees binary or XDR magic bytes, it will then treat the entire file as if it was the binary or the XDR format. However, you can see here that there's 2 or 3 bytes. And that's because there's a lot of components in R from when R was first created. So because R was originally created as an ASCII format, there were oftentimes new line characters at the start of these files. So if there's a new line character, it will actually try to read 1 more byte and then see if it's an ASCII format. So as you can see, a lot more inconsistencies. What we then do is, once we actually figure out what the format type is, we then change what our actual size is that we read. So you can see here in the really small text underneath, we have that the byte values are done in either the binary or the XDR format. And that's because an integer in either of those is going to be 4 bytes. However, the ASCII format is actually 126 bytes, because what they do is they just read in 126 bytes, do A to I, and then use that for any integers. So once we actually know the format type and we know, what length we're using for all of our data types, we go through, we get the version number, the writer version, and the minimum reader version. And then we check to see if the version number is greater than 3. If it is, then we check our encoding name length, and then we actually read the encoding name. And for those of you that might want to try to find some CVEs, we actually noticed that there are possibly some crashes. I'm not saying anything, if you mess with the length because of some allocations. And then once we have all of our data parsed, what we do is the rest is that serialized data, so it's the bytecode that actually goes into the RDS virtual machine. So the RDS virtual machine has 36 possible bytecode instructions, which create a bunch of objects. So the RDS virtual machine actually creates objects, whereas the R virtual machine is just instructions, and it works, or the Pickle one works on the stack and the memo. And there's a lot of different objects that we can have. The first is that we have these lists, and as you can see, there's quite a few different data types that you can have in the list. So you can have logical, so that's your true, falses, integers, numerics, your complex numbers, your characters, and you can even have just raw bytes. You can also have symbols. So a symbol in R is something like the system function. That would be a symbol. It can also be variables that are in the environment. You can actually generate entire functions using the RDS virtual machine. These are obviously not executable within the RDS virtual machine, otherwise our talk would be much shorter. And then you have environments as well. And what's interesting about the RDS virtual machine is that whereas Pickle will just run through all of the instructions, and when it sees the stop instruction, it will take the last value off of the stack and return that, the RDS virtual machine uses a recursive function call. So we actually go into this read item function, and as soon as the top level read item returns, that is returned back to the user, and then all the data after that is ignored. So if you have extra data and the virtual machine is done, that's it. So it doesn't just let you keep running. So any payloads that you have to do within one complete object. Where with Pickle, we can put something in between and actually return something that was meaningful for the user. And then all of the instructions start with the same 4-byte flag. So for ASCII, that's the 126-byte flag, which is quite long. But our 4-byte flag, what we do there is it's encoded with all the necessary data that's then followed by a variable length of data for whatever instruction you have. So let's look at how this flag is unpacked. So we can see here that the type of the instruction is just grabbed from there. We also have something called levels, which is used for characters. You'll see that later on in another slide. We can set whether or not this object is actually an object, whether it has attributes, and whether it has a tag or not. So just like with Pickle, and as you might have noticed, there are some instructional quirks as well. The first is that we have this bytecode instruction. So most of the R instructions will return one object and only do one thing per instruction. However, the bytecode instruction is basically just like a header, and it requires a strict format to be followed after that. So that means once you see the bytecode instruction, it will try to read a list off for any constants, which are then a list of objects, and then it will try to read off just raw data bytes. So you have to have that format, otherwise it will crash. We also have generally any objects returned from the RDS file and the deserialization process are S4 objects. However, what you can do is you can return a vector with that object set to true, and it will actually create an S3 object, which is an older version of R objects, which aren't supposed to be used in the R virtual machine. And then we have just a list of objects. We have some instructions that have lists of objects. And these, the way that they work is when it starts having the list, it will keep running through in a while loop until we see a stop instruction. And then it will get out of that function. So there's a lot of instructional quirks. And what instruction do we actually use to do our exploit? R has a system called lazy evaluation. And lazy evaluation is the strategy where expressions are not actually evaluated when you first save them. So that means that if I have x equals a is 4, and then I do a plus 1, so a is now 5, and then I access x is actually 5, not 4, because x was not accessed until after a was updated. So that also applies to function arguments. So if I pass that evaluation, or pass it down into a function, if it won't actually be evaluated until the function actually accesses that variable. And once the argument is accessed, the stored expression is evaluated in the environment that is set by the promise object. So for the promise object inside of the virtual machine, we have 3 components that are required to actually build this object. We have the expression, which is the unevaluated R expression that we actually want to run. We have the environment, so that's the environment that we actually want to run the expression in, so all the variables it is going to use have to be in that environment. And then finally, we have the value that we're actually going to store the expression to. When we were first trying to create our exploit, I was actually looking in, and promise object was one of the first things I saw and tried working with. And one of the things I tried doing was, if there was a variable already in the environment, I tried setting the environment to the current environment and then setting the variable to, or the value to a value that existed. However, that didn't work. So what we ended up doing was we looked further, and so this is actually our exploit. And one thing, this is using a compiler that we're going to open source as well. And so remember when I said that there's certain instructions that start a list? Any arguments passed in have to be in reverse order. So in this case, we have the value expression, or value environment expression. So what you can see here is that rather than actually setting a value from the environment, we set it to something called an unbound value. And what that means is that the value is whatever you store it as. So that means if we do a is equal to read RDS, that a is the value that once that's accessed, that is going to actually execute our expression. Once we have that, we have the lengs instruction, which is just used for expressions. So as you can see, we use symbols, and we get the characters. So we have system there. And the 64 value that you see there is that levels that I was talking about. So it's just a value that's checked later on. For most things, you can just use 64, and it'll work. And then once we have our system, we then have another list. That's going to be our tuple that we pass to our system call. And here we simply have echo and then pwned by HiddenLayer. So now let's look at how does this actually work. So as I mentioned earlier, the unbound value, what that means is that anything, or whatever it's set to, is going to be treated as the value from then on. So as you can see here, if we have A is our value. As soon as A is accessed, we see pwned by HiddenLayer. So the actual type of A does not matter. So as you can see here, we can set it to B, and then B times 1. We still have pwned by HiddenLayer. We can pass it into functions, and even if it's not what's expected, we see pwned by HiddenLayer. And then my favorite is if it's actually expecting an object, because a lot of times an attacker doesn't have control over how something's used. So if there is an object that is being accessed from this read RDS, even if you're not returning an object, and even if it doesn't have the parameters, it can't access the parameters and components of the object without first doing the lazy evaluation. So that means no matter what you have and no matter what crashes happen, your code is always going to be executed first. So that means that the payload will run. So obviously, we went through and we did responsible disclosure. So we went to R. And actually, I have to give a shout out to R, because they actually patched the vulnerability in a month, even though we gave them a 3-month heads up there, which is one of the faster turnaround times, which was great. But what R did is they added this function to check whether the topmost returned value was a promise object. And the code here is actually the code from the R virtual machine. And you can see that it just checks to see if the type is equal to a promise. However, there were a few problems with that. We discussed it with R, and R wanted to keep going forward with what they had done. But bypasses were found once the research was released. So some people were nesting the promise object within an environment, because then once the environment was loaded into the main environment, the promise object was still evaluated. And then some people actually found ways to run the code within the virtual machine without ever returning. So, I mean, once you have a machine, or once you have a virtual machine that executes code, there's really no way to secure it properly. And then what was also interesting was that this patch was only added to the read RDS function, whereas there were a lot of different functions that used the RDS virtual machine and loaded RDS files in the R ecosystem. So we wanted to go through and show R, and we wanted to show R that there was an issue with this in a way that once we published, people wouldn't use it if it didn't get patched. So we decided to just try to see if our packages could be exploited. And our thought behind that was people hopefully aren't just going to download random packages and run them for the most part. So it was a good example for us to kind of show. And unlike just the regular RDS function, our packages use something called lazy load, which, lazy evaluation system, to load all of the data into memory from an R package. So lazy load was filled with inconsistencies again. What you see here on the left is you see the R versions of lazy load. So if you're ever using R, you can just type the function name and it gives you all the R code, which is awesome. It's really nice because you don't have to go hunting down into files. But as you can see, we call lazy load db fetch. And then in lazy load db fetch, we have a primitive. Anytime you're doing anything in R, if it calls primitive, it will then call into the C code. And then here on the left, we can see do lazy load db fetch, which is our C code. And what some of you guys may have noticed is whereas the patch for read RDS checked to see if it was a promise object and returned an error, in here, if there's a promise object, we run eval on it. So it's not ideal. So we don't even have to wait for the promise object to propagate up, because as soon as the promise object exists, it will be executed. So where do people actually get these R packages? So mainly people get R packages from the Comprehensive R Archive Network, or CRAN, which is about 21,000 packages. So that's the official R package list, and that's what you can just access. Obviously, there are third-party sources for packages like RForge, and then there's also package lists that are very specific to certain types of projects or fields, like bioconductor, which is biostatistics work. And what you can see here on the right is we have a nice little tree of just what an R package looks like. So this is compiler. This is one of the built-in R packages. And as you can see, it's filled with RDS files, which R is already a problem. But if you look into the R folder, you see that we have a compiler.rdb and a compiler.rdx. And those are the main workhorses for actually loading an R package. So looking into these files, an RDX file is pretty much just an RDS file, just with a different file extension. And what it is it's a vector. So we have just a vector. It has a bunch of the names of just the functions, the environments that are within the R package. And then it has an offset from the start of the file and then the length of data. So let's say I want to load function A. The R virtual machine uses readRDS to load the RDX file. It then goes through, it checks to see which one is A, grabs the offset. It then loads the RDB file, goes to that offset, and then extracts the length of data from there. And then that length of data from the RDB file, and the RDB file is just a blob of data, so just lots of different consecutive blobs. So the first 4 bytes are the decompressed length. And the decompressed length here is actually used for allocating space before it decompresses the serialized data. If you guys want to look there as well. And then they have the actual compressed serialized data, which is then decompressed, and then we actually load it into memory. So obviously, we wanted to go through and we wanted to see, we had this way that we could see that RDB files were potentially malicious, so those R packages. So we actually went through every single R CRAN package and checked to see if there were any promise objects on that top level. And while we didn't find anything malicious, we actually did find quite a few projects that did use the promise object at the very top. So we just wanted to talk about that as well. So here is Datos. What you see here is a screenshot from our CRAN, so just gives some package information as well as their GitHub. And then we have a snippet of the code that actually generates the promise objects in the RDB file. So delayed assign is generally used to create those promise objects in memory. So so that's what we looked for. And what you see here is that there's a bunch of delayed assigns in this package. And what they do is they load in a script, a text file, parse that as R code, and then run eval on it. And this all happens as soon as the R package is loaded, before you even access a specific function. So it's something that we wanted to look into, see if it was malicious. While this package was not malicious, what it did is it loaded in some data, and then it just ran. It could very easily become malicious if somebody can just sneak in code that won't even run when you call a specific function, but as soon as you load the package into your environment. So as Tom mentioned, we had 2 different open source projects that we will be releasing, and I love their names. The first is HiddenPickle. So HiddenPickle will actually have 4 main components, and this link is live, so if you do want to use the tool, it's all on there, and that is all the assembly that Tom showed. So the tool, as I mentioned, has 4 parts. The first is a disassembler, which allows you to disassemble the pickle files without running arbitrary code, but it also handles files that are missing the proto instruction, missing the stop instruction, so you can really disassemble anything that you want. We have a patcher, so let's say you don't want to compile an entire Pickle file by hand. You can hook specific instructions to alter their values, or you can add or remove instructions based on patterns in the file. We have a compiler, which allows you to compile Pickle files either programmatically or by hand. And then we also allow you to have complete control over the generation of those Pickle files. So with this tool, you can actually build every single attack that we have showed you today. And then finally, we have our dynamic function Pickle, where it was that generate programmatic Pickle, where you just give it a function, and it will run that function as a Pickle itself. And then we also have hidden promise. So hidden promise has 3 main components. That link is also live if you want to go to it. The first is a disassembler. So it allows you to disassemble those RDB files. And whereas Pickle, our Pickle disassembler just gives you straight disassembly, the R hidden promise will actually convert all of the R objects into Python objects so that you can traverse them and easily check values. We also have a package explorer, which allows you to automatically disassemble RDX and RDB files, as well as scan RDS, RDX, and RDB files for that malicious code. And then finally, of course, a compiler, which allows you to compile new RDS files, as well as inject code into existing RDB files. So rather than having to build an RDB file from scratch, you can take an existing RDB file, select a function or variable that you want to change, and then you can inject whatever code you want into that. So we have our nice little sound bites as well that we want you to come away with. The first is, please just ensure that your deserialization methods match your actual needs. So, hey, Tom, if we have a project that uses Pickle for like lists and strings, what can we use?
I mean, JSON would be a very good start for a lot of smaller data.
You don't need a Pickle for just things like that. Next is attackers should scrutinize any deserialization processes for potential exploits, but specifically those that actually have an entire VM, aren't like a dumb format, but run code to deserialize. Yeah, those are fun. So, Tom, what do you normally say when you see a deserialization process with a virtual machine?
Well, I know you get very excited.
I do get very excited, yeah. And then finally, protect file formats. To protect them, you really need a deep understanding of their internal workings. A lot of people will just, or a lot of projects will just try to scan basic patterns. So we've seen a lot of open source scanners for Pickle. They just look for very specific strings in it, and they can be bypassed fairly easily. And I mean, Tom, how many ways have we found to execute, just in built-in Python functions, execute code?
I mean, in the standard libraries, a couple of hundred, and then with some of the third parties, a few hundred more.
Yeah, so imagine trying to come up with every single Python function that could potentially execute code when there's hundreds of them, and not just the functions, the classes, sometimes when you instantiate them, run code. Well, thank you very much for coming to our talk. Anybody who has Q&A, we have about a minute and a half left, but then we can also move over to the wrap-up room if you want to come there as well.
Oh, question over there.
Please come to the,
yeah.
Yeah.
So for, I mean, I scanned Pickles. I think most models hosted on Hugging Face have Pickle files, right? So they build safe tensors for that. Do you have something like that for R, or did R come up with something?
So R added the patch. And so R did a similar approach to Python where they put the warning on now. So people shouldn't deserialize untrusted data, which is the same with Pickle. You really shouldn't. And then as for R packages, it's what they say is make sure you review the code before you actually load it into your system.
Yeah, that makes sense. But have you seen the safe tensor files? Do you think there are ways to get code exec using them?
So the safe tensor format is actually really nice.
Yeah.
They do a really good job. So it's, as I said, like a dumb format, as we were saying, where it just loads the data and nothing else, and it's just integers or floats. However, we have seen and published research where converting over into the safe tensor format, you have a lot of vulnerabilities in there. So Hugging Face actually had a service to convert like PyTorch files into safe tensor files, and that was exploitable and could potentially impact other users as well.
Yeah, interesting. I think so. I work at Databricks. I think we do the same thing. So I better check that.
Yeah. Thank you for your questions.
Yeah, thank you. Cheers.
And then we'll move over to the wrap-up room if anybody wants to come, since we're out of time. Thank you for coming.